Hello everybody, my name is Hunter Ream, and I will be talking to you about Generating Functionology by Herbert Wilf. In particular, we're going to be talking about section 1.5 on binomial coefficients. So first off, I'd like to ask you a question. Question is, the question is, how many subsets of the set 1, 2, 3, 4 are of size 2? So let's write that out. How many subsets of 4, so this is equal to the set 1, 2, 3, 4 are of size 2. Let's redo that here. So we can actually list these explicitly. So 1, 2 is a subset of 1, 2, 3, 4. 1, 3 is a subset. Let's see. 2, 3 is a subset. And then 1, 4, there aren't too many of these. 2, 4, and I believe the last one is 3, 4. Okay, so I wrote these out in a very specific way. I want you to note that the first 3 of these 3, do not contain 4. They do not contain the last element of our set. They do not contain 4, and these, every single one of them, does. So these do contain 4. So we can actually count all of these subsets by first considering all of the subsets of 1, 2, 3, 4 that don't contain 4, and then add the number of sets that do contain 4. Okay, so in this, the answer to this question is 6 because we were able to write them all out. But let's say we ask this question, a more general question. One might say it's a little bit harder. Is how many subsets of n equal, this is the set 1, 2, 3, all the way up to n, are of size k. So we don't actually know the answer to this question right off of the bat. So what we're going to do is we're going to suppose there are fnk subsets of n that are of size k. Now this doesn't actually do anything for us right off the right. I mean, fnk, it's no better than just saying we don't know the solution, but what we're going to do is we're going to try to come up with a recursive formula for fnk. And to do that, what I want you to imagine is all of these subsets of size k are laying in front of us. So I'm going to draw a little picture here, actually I have a nice, here, let's say we have all of the subsets of size k are living in this box somewhere, right? So they're just all laying in front of us, and I'm going to bisect this box and say on the left-hand side, which is right here, we're going to put all of the subsets, just like we did above, that do not contain the last element. So over here, these do not contain n, and then on the right-hand side, they will contain n. Do contain n, okay? And so now we can actually ask the question, how many of the subsets will not contain n? Okay, well, if we know for sure that these subsets don't contain n, then we are only choosing from n minus 1 different elements. So we can actually write this using the same notation, this fnk notation, right? But instead of choosing from n things, we know we're not going to have one of the elements, so we're only choosing from n minus 1 things. But it's still true that we need to choose k elements. Still need to choose k elements because there's no decided element inside every subset. Whereas if we go to the right-hand side, we know that n will be in every single subset. So it's true that we only need to choose from n minus 1 things still. Because n, we're not going to repeat this. But since n is chosen and is in every single subset, we only need to choose k minus 1 more things to complete that subset. So now we have this recursive formula that we can actually write out. So here, let's go to the next page here. So we have the recursive formula, which would be fnk is equal to fn minus 1 k plus fn minus 1 k minus 1. And so now we have a recursive formula, and this is exactly what we need in order to utilize the generating function theory that we've already developed in the previous sections. So I'm just going to draw a line here because what we need to do, fix n to be a positive integer. So we're going to assume that n is some fixed positive integer and consider the sequence where the k's range from 0 to infinity. Consider the sequence fn k, where I'll specify specifically that n is fixed. The k will start at 0 and go to infinity. And we'll define, using this sequence, we'll define a generating function. Define the ordinary generating function Bn of x. And so we're going to let k range from 0 to infinity, have the coefficients be the elements of our sequence, and those will be the coefficients on the x to the k. So this is our generating function, and what we're going to want to do, I'm going to draw another line here. So now we're going to go back. Let's rewrite our recursive formula. I know I have it written above, but we know that fnk is equal to fn minus 1 k plus fn minus 1 k minus 1. And now what I'm going to do is I'm going to multiply by x to the k on both sides. Where in our case now, k is just some integer, and it's always been some integer. Let's take x to the k and multiply it on both sides. Whatever k is, this is still going to remain an equality. Just going to multiply through. I'm going to distribute the x to the k to both of these right away. And one thing that we can do is, since the left-hand side here is always equal to the right-hand side here for every single k, then we can add up all of the k's. We can actually range from k. Now here's the subtlety here. We're going to range from k equals 1 to infinity of n k x to the k. And we're going to do this everywhere. We're going to range from k equals 1 to infinity for all of these. And the purpose of this is so that we can make these look closer to our generating function. So let me finish writing this. Fn minus 1, k minus 1, x to the k. Okay, so the left-hand side looks very, very close to the generating function that I've defined above. It looks very close to Bn of x. The only thing is I started at k equals 1, whereas the generating function starts at k equals 0. To counter that, what I have to do is, I really want it to look like this, right? I want 1 to be in there. And by the way, when I say 1, that's when k equals 0. We would ask ourselves, what is fn 0? Well, fn 0 is going to be 1, because that's asking how many different ways are there to choose 0 things from n things, and there's only one way to do that. You just choose nothing. But, so we want that 0th term to be in there. But we can't just add 1 just cuz. What we have to do is we have to add 1 and then subtract it off, right? So this is what I call cleverly adding 0. Okay, we're going to cleverly add 0, but then this piece right here, which includes the 1, that is identically Bn of x. Okay, so I'm going to write that now right here. This is Bn of x. This is the part that I put a bracket over, but then we have to subtract the 1 off. Okay, well then this is going to be a similar thing. So now let's look at the next piece is exactly the same thing, except for here we add an n. Now it's just n minus 1. Luckily, this k matches the exponent on the x. So we have almost exactly our generating function. We need to add and subtract 1 again. Oops. Yeah, so we do Bn minus 1 of x this time, because we have an n minus 1 right here. But of course we have to add and subtract 1 to counter this starting at 1 and our regular generating function starting at 0. So we're going to have to subtract 1 here. Now this one is the last piece is a little bit trickier, but what we need to happen is we need this k, which is k minus 1, to match the exponent here. And in order to make this a k, we can't really change this portion, so what we're going to do is we're going to try to change the exponent. Yeah, no, sorry, if I just factor out a single x, then I have to counter that by saying, okay, that's k minus 1. So I could factor that back in and get back to where we were, but now we're exactly where we need to be, because this, the exponent, matches this k right here, k minus 1, great. And now we also have to note that our n is n minus 1, so this is going to be x times Bn minus 1 of x. Now you might be thinking, why didn't we have to add and subtract 1 here? Well, if you notice, when I put this k equals 1 in for k, it immediately starts at 0, which is what I need in my generating function. And the exponent in this will be 0 right away. So we already are keeping track of that by starting at k equals 1 here. So that's good. So now we have a new formula here, which I can actually solve for Bn of x, just using basic algebra, and say Bn of x would be identically equal to 1 plus x times Bn minus 1 of x. And if you don't believe me, it's pretty easy to work out. Just cancel the 1s and factor out a Bn minus 1 of x. Okay, so now that we have that, that's really nice, but that's more of a recursive formula for our generating function. That's not what we want. We want an explicit formula for our generating function. It is not too hard to come up with exactly what this generating function looks like. And this is what we're going to do. Let's just start. Let's go to a new page here. And yeah. So here's an example. Let's look at B0 of x. So when n is equal to 0. Well, Bn of 0, remember our generating function is identically k equals 0 to infinity of f, in our case, 0k. Of x to the k, which, let's just write out a couple of these terms. This is f0k with, that's just a constant, plus not k, f0 0 plus f0 1 x plus f0 2 x squared. Okay, now we probably get the point. But we need to ask ourselves, remember, what does this mean? This means how many different ways can we choose 0 things from 0 things? And we can actually do that in exactly one way. We can just choose nothing. But then once we advance and we ask ourselves how many different ways are there to choose one thing from 0 things, then there's a problem, because we can't choose one thing from 0 things, so this coefficient will indeed be 0. So this whole term will be 0. And similarly, if we want to choose 2 things from 0 things, we can't do that. This is going to be 0 as well. So all the terms after that will be 0. Okay, so we found that B0 of x is 1. And actually, we have that B1 of x. We already have a recursive formula for this. We said that we said that B1 of x is going to be equal to 1 plus x times b0 of x. So then, we know that this, well, b0 of x is just 1, so we know that b1 of x is 1 plus x. And one more example, and this will really drive it home, I think, is if, well, b2 of x is 1 plus x times b1 of x. Of course, b1 of x is 1 plus x, so I'm going to rewrite that, but b1 of x we said is 1 plus x. Well, this ends up being 1 plus x squared. And in general, bn of x, and you can show this by induction, we have the base cases, just inductively you can get that bn of x is 1 plus x to the n. And you can see that because this exponent matches exactly the subscript here. And you can prove this by induction. So we have an actual closed form for our generating function, for our ordinary generating function. And that is great because, now there's one thing that I'm going to have to recall here. Let's recall something that maybe we haven't even thought about since taking some calculus class, maybe calculus 2 in college or high school or whenever you took it. And we have to recall that the Maclaurin series expansion of a real valued, a real valued function, it's just a function, just a real valued function f is, f of x would be equal to the series k equals 0 to infinity of the kth derivative evaluated at 0 all over k factorial times x to the k. So it is a power series, but it's a very specific power series. And it kind of looks maybe like it looks like a generating function for something. And it kind of is. But we have a Maclaurin series, so we're going to be using this. All right, so I can actually write. So note, actually, let's go to the next page here. Let's go to the next page. So, oops. All right. So, note, bn of x is equal to 1 plus x to the n. And we can actually use the Maclaurin expansion to get some of these. We can get an expansion for this if we take the derivative of, the first term is actually just evaluating this at 0. So we're just going to do that. We get 1. And the second term says you take the derivative of this and then evaluate it at 0. And so if I take the derivative of this, I have to bring this n down in front and then put a 0 in for x. And what do I get when I do that? Well, it's just plus n, and then I have to multiply by 1, and that's the coefficient on x, and of course I divide by 1 factorial. And I'm going to continue in this way. So now, if I take the second derivative, I bring this n down in front, and then I subtract 1 from this, right? But then when I take the second derivative, I have to bring an n minus 1 down in front. So my coefficient ends up being n times n minus 1. And this time that's the coefficient on x squared. And this is all going to be over 2 factorial. I'm just working through the Maclaurin expansion. But the general this continues. The general formula for this, if you're not seeing it already, is I'm taking what looks, and this is going to happen again, right? I'm going to have to take an n minus 2 and bring it down in front. And for the next term, I have to continue doing this. So what's happening is I'm taking n factorial and dividing by n minus k factorial right there. So this ends up looking like k equals 0 to infinity of n factorial all over n minus k factorial. And this is the general term for what's happening in the numerator here, and what will happen down the line. In addition, we have a k factorial in the denominator that comes from the Maclaurin expansion. So, and this is always going to be the coefficient on x to the k. And so from here we can actually see that, well, remember, let's leave some space for this, Bn of x was equal to, initially we defined it to be equal to, k equals 0 to infinity of fnk of x to the k. But we just figured out, just right above, that it's equal to k equals 0 to infinity of n factorial n minus k factorial of x to the k. And now we can just equate the coefficients. When I say equate the coefficients, I mean look at the x to the kth term here and the x to the kth term here. We can actually say that the coefficient on x to the k here will be equal to the coefficient on x to the k here. So fnk is identically equal to n factorial over n minus k factorial. And this might be a familiar formula. This is n, choose k. This is the formula that we use. And this is the formula for the binomial coefficients. So thank you for listening.